All right, so what we're looking at today is we've been going over work and energy here for the past week or so. So now we got to make sure that this actually works for real, okay? And that the relationship between force and distance and work is what we think it is or works the way we think it does, okay? So we're going to do a very easy lab in order to test that. Okay, this will kind of be the warm-up lab for the energy conversion lab, okay, that we'll be doing a little bit later. Okay, the energy conversion lab involves us actually doing exactly what we're going to do today with the rubber bands, except we'll load the cars into the rubber bands. We'll have these little dynamics carts that we shoot with the rubber bands, and then we measure how far they go, and we figure out how much energy actually ended up in the cart. That's what we'll be doing next. This is kind of the build-up to that. All right, so the problem that we're investigating, we want to figure out how can we determine the amount of work done on an object. Well, we've been doing this whole thing for a week. So I think we have a pretty good idea of how we might do that. Okay, it might have something to do with that work energy theorem thing. Okay, now for this lab, what we're going to be doing is we're going to have a rubber band. Everyone's going to get the same kind of rubber band, right? And it's going to be stretched between the legs of two desks. Two desks, not one desk. The legs of one desk are way too far apart for these little rubber bands. Okay, so you'll need two desks for this. All right, so we'll stretch them in between the desks, and then we're going to pull on them with these spring scales. Right? It's not a technically difficult lab. All right, so what we'll do is we'll have the rubber band stretched between the desks, and then we're going to decide on a few lengths. Okay, we're going to choose the lengths or manipulate the lengths that we're going to pull the rubber band to. The length might also represent distance in that formula up there. Is that clear enough? Yeah. Okay, all right, so we're going to choose the distances and we're going to pull the rubber band to those various lengths that we've decided on, okay, and we're going to record how much force is required for each distance. All right, so we're measuring force, okay, we're choosing distance, we're measuring and recording force, okay, as a result of that. Okay, since we have no way to actually measure work, we have to measure the force, and then we can go and calculate work from there. Everyone with me? Okay, now, for our controlled variables, basically anything that could affect the tension in the rubber band needs to be controlled. I'm going to give you one of them because it's the most important one and it's an important part of doing the procedure correctly. The distance between the desk legs has to remain the same throughout the entire lab. If the desks move during the lab, you'll have to start over again. Okay? The reason for that is it will put a different amount of initial tension in the rubber band if the desks move. And as a result, the band will already be stretched a little more or less than it was on previous trials. Okay? Everybody follow me there? So our desks have to sit still, which is why we're going to be in groups of 3 or 4, because 2 of you have to sit in the desks to make sure the desks don't move throughout the entire lab, okay? And 2 other people will be doing measuring and pulling and whatever else, okay? So 2 of you get to be pylons for this lab, okay, and hold down the desks so that they don't move. All right, so groups of 4 are kind of ideal here. I mean, you can get by in a group of 3, but groups of 4 are ideal. All right, so there's 2 supervisors and, 2 workers. Government job, okay? All right. Everybody with me there? Okay, so that's one of the control variables. You guys can figure out the others. Remember that you need 3. Okay, for our hypothesis, okay, we want to generate a hypothesis that explains how, using the materials below, we can calculate the work done on an object. So, if part of our hypothesis, should probably talk about what's work. Okay, and I don't mean like quote me the formula. I mean kind of what we've been talking about, kind of our definition of work would be a better idea. Okay, the and part's going to describe the experiment, same as always, and the then part should answer the problem. Now, in your lab report, I can't remember if I put in the correct distances. We've done this lab a bunch of times, and you certainly can't stretch this rubber band as far as the procedure says to stretch it. You'll never stretch it 20. Well, you might be able to stretch it 20, but you're not going to get good data that far. Okay, so we don't have it in here. It says here 5, 10, 15, and 20 centimeters. There's just no way. Okay, if you stretch this thing, like, that's what you guys are going to have to do. That's about 20 centimeters. There's a certain range over which a rubber band stretches linearly. And once you get beyond that, it becomes more like trying to pull on a rope. It ceases to be elastic and you're just trying to break it. And then your force goes from being nice and linear on a graph to suddenly just going into a big curve, right? If we get to that point, we're beyond the normal elastic range and we're no longer getting a good work-force relationship, okay? So the distances I would recommend, and you might just want to put these into your chart, okay? I would say go with, let's say like every 2 or 3 centimeters, starting from 3, 6, 9. I'd say that's a better one. Until you have, I think we want 5 distances on this graph. 6 distances on this graph, okay? Could one of those distances be 0 and 0? I would say that's a good idea, okay? So really you only need 5 distances. So I'd say going up to 15 centimeters by 3s would be lots, okay? Okay, now we're going to forget about this because this was me reminding myself to go to 15 centimeters and not 30. I don't know why I didn't just erase the 30, but anyway. Okay, we have one problem with our spring scales. When the school was built, we ordered, of course, all new equipment for it back in 2005, and we ordered these spring scales then. And when we got them, Mr. Dickey and I were all happy because we looked at the boxes, and the boxes showed the spring scales we ordered. They have grams on one side, and they have newtons on the other, which is exactly what we wanted. We were very disappointed after we had confirmed that we got what we wanted, and then tried to do our first lab 3 months later to discover that what was in the box was not the same as what was on the box. There's no newtons on these spring scales. So we called Boreal, and we tried to get them exchanged. And we're like, you didn't send us the right scales. They said, yes, we did. We said, no, you didn't. Back and forth. We said, look, the boxes are right. They have the picture of the spring scales that we wanted, but what's in the boxes is wrong. Tough luck. You signed the thing that said you got what you wanted. So we're stuck with them. They subsequently have gotten none of our business. You got certain rights as a consumer, certain powers. That's one of them. Anyway, it's not too big a deal. All you're going to do is take the reading in grams and divide it by 10. I mean, really, we should be dividing it by 9.81, but we're going to make things simple. We're just going to divide it by 10, and that'll be in newtons, all right? So whatever it reads in grams, divide it by 10, okay? And you've got it into, sorry, not by 10, by 100. What am I saying? By 100, not by 10. By 100, and you'll have it in grams, in newtons. Holy smoke, it's Monday, okay? Take whatever it reads in grams and divide by 100. Okay, there we go. All right, and then you'll have your proper reading in newtons there. Okay, everybody good with that? Please ignore the ounces side. No one uses ounces. Okay, I don't know why that's even on there. But okay. So when you're doing this, okay, and you've got this stretched between the 2 chair legs, so you'll probably use like the back leg of one desk and the front leg of another. Put them just far enough apart that it's not slack, okay, that the rubber band isn't slack, just so it's just taut, okay? If you have it stretched, this isn't going to work very well. So just enough that it's kind of like that. Okay, everybody with me? Okay, you're going to pull both sides of the rubber band with the spring scale. Okay, so you have to get the whole rubber band in the scale when you do this. Okay, pull it nice and easy, okay, to the specified distance and hold it still, okay, so that your partners can read the scale. It's not tough. All right, so collecting the data is going to take you 5 minutes, okay, and then you'll have the rest of the class to start writing up the report. Okay, so you should get a pretty good start on that, maybe even get it finished because it's not terribly difficult. Okay, now the analysis is written poorly, and I'll take blame on that because I copied it from somebody. Oops, that's out loud, wasn't it? Anyway, okay, it's from the old Science 10 textbook. We paid for that. So anyway, the analysis is written poorly, and it's really confusing. Okay, so I'm going to kind of explain it to you here. You might want to make a few jot notes in your analysis to just kind of remind you of what everything means. Okay, in analysis question number 1, well, first off, you're going to have to build a graph. So you're going to need Google Sheets. You're going to have to build a graph of distance versus force. Okay, for this lab, it's going to spit out a nice linear graph for you, which you will insert. Okay, same as you have all the other graphs we've done into your Google Doc. Okay, so we want to calculate the area beneath the line of our force distance graph. So our force distance graph is going to look something like this. And we're going to have a triangle. All right? So we're going to calculate the area underneath it. Because each time we do a trial, we're using more force and more distance. Okay? So each time we do a trial, are we putting more potential energy into the rubber band? So each trial, are we doing more work? Yes. What we want to find is the total work, okay, over like the whole kind of experiment here. Okay? That's why we're calculating this. Everyone follow? All right, because really when I calculate this, what am I calculating? I'm multiplying base, distance, times height, which is force. Okay, I think you guys can figure out what you're calculating when you multiply those two things together. Okay, all right. So that's what number 1 is talking about, is calculate the area underneath your line. Okay, and they talk about this average force thing. Well, it's just like when we did the area underneath the line on a velocity versus time graph. We were using the average velocity. Okay, that's why we went base times height over 2. We're kind of doing the same thing here. So this tends to confuse people. So I would say, you know, read it, because obviously it's got this force average times distance and it helps you figure out technically what you're calculating, but really you're just doing this, okay, half the maximum force exerted. Calculate the area under the line. Don't overthink it. They just word it really poorly. Okay, all right. Number 2, okay, what does the area under the force distance graph represent, and how do you know? I'm going to want a pretty good explanation there because I kind of gave it away already, okay, but I'm going to want a pretty decent explanation there, and I would work into that explanation something about potential energy, okay, elastic potential energy in the rubber band, okay, because that kind of fits with our hypothesis, okay, when we define what work is, okay, that's got to work in there, okay. Okay, then you'll have your conclusion and evaluation, same as always. All right, this is going to be due on Thursday, okay, because of course the intention here is that you're going to get it mostly done in class today. All right, questions on that? All right, get yourself a group, come up here, grab rubber bands, spring scale, okay, all that good stuff. Oh, sorry, when you grab the spring scales, they are somewhat adjustable. This little metal tab here at the top allows you to pull the scale up and down. So you probably don't want to start with it like that, where it's reading that even with no force on it, it's already at like 100 grams. Okay, so just make sure that when you start, you've got that scale pushed so that the little bar is right on 0. Okay, they get bumped around, so that gets moved. So just check it before you start. And no snapping each other with the rubber bands, please. Okay, come and grab your stuff, guys. On this graph here, everything in the procedure has said centimeters, centimeters, centimeters. Graphs in meters, because if you multiply force times distance and it's in centimeters, you're not getting what you think you're getting. Okay, so make sure you start off that, you know, your first distance there, 3 centimeters, is 0.03 meters. Okay, make sure that that's pretty important. Your calculations will be wrong.